Hello, good morning, good afternoon.
Good evening, ma'am.
Good evening हो गया?
Yes, ma'am.
Really?
मैम सर ये जाने हो चुकी हैं.
Ah, yes. So how are you?
Ma'am, I'm good. How are you?
I'm good, thank you. Okay, so
Am I the
let's
only one in the class?
let's see. Other people will be joining, so let's give them a few minutes. Okay.
Yes, ma'am. So, ma'am, we will be having Zoom classes every day now.
Every day, like according to the timetable, right?
Yes, ma'am.
Yeah.
Yes, ma'am. Did we have a class on Tuesday?
On Thursday, I gave them the handout. There was only one girl in the class. So
Yes, ma'am.
I gave her some material that was uploaded to WhatsApp as well.
Yes, ma'am.
Yeah.
So I thought maybe you have given lecture on Tuesday.
Hmm. So Asad is here. Hello, Asad. Am I recording? Hmm. In progress. Hmm. Return to meeting. Yeah. Okay, so we have Shurjeel and Asad. So let's look at the other people. PNG. Hmm. Why am I not able to see? Hitting control. Mhm. Continue. More. Mhm. Yeah. Hello. Yes. Okay, now we have Ramin. Hello, Ramin.
Hello, ma'am.
How
How
are
are
you?
you?
I'm fine. How are you?
I'm also good.
Great. Okay, Asad. Hello, Asad.
Hello, ma'am.
How are you?
I'm doing great, ma'am. What about you?
I'm fine, thank you. So we have three students, so let's wait a few minutes to allow the other three to join as well so that we can start. Okay? So what do
Sure,
you
ma'am.
see
Yes,
right
ma'am.
now? What do you see? Durdana is here. Okay, so let's invite Durdana. Recording चल रही है. Okay. Hello, Durdana. Okay. So who else will be here? Hello, Durdana.
Hello, ma'am. How are you?
you?
I'm fine, ma'am. Thank you.
Good. So are you in Lahore?
Yes, ma'am. I'm about to leave for home.
Okay. Right. Okay. And there was another girl, Ramin. Are you also in Lahore?
Yes, ma'am.
Okay, good. So do you plan to stay here?
No, ma'am, I will leave tomorrow.
Okay, good. So two people are missing, but I think we can start now, right? Okay. So if there's someone in the waiting room, you can tell me. I think there's no one in the waiting room. Okay. So we are going to study today the last topic of chapter 3, okay, which is nuclear excited states, right? Can you see my board?
Yes, ma'am.
Good.
Yes, ma'am.
So this is what we are studying today, okay? So you're familiar with the concept of excited states, right? You remember that in an atom there are excited states, right?
Yes,
We know
ma'am.
that an atom generally has excited states. Okay, so similarly, we have the concept of excited states inside a nucleus. Okay,
Yes.
let's see the participants. Okay, someone just dropped out. That was Asad. Okay, right. Okay, so similarly, we have that nuclear structure can be studied with the help of studying the properties of excited state. So nuclear excited states help us study nuclear structure. Okay. Okay. And nuclear excited states, these states are, we can now rub this. Okay. These states, nuclear excited states are, they are unstable. Okay. And they decay rapidly. To the ground state. So in atoms, we make excited states by moving individual electrons. You remember the concept of atomic excited states or atomic excitation. So can somebody explain that? What is atomic excitation? Yes. What is the atomic excitation?
When an electron moves from lower orbit to an higher orbit.
Yes, right. Okay. So in atoms, we have excited states when individual electrons move to higher energy orbits. The same can be done for individual nucleons. So in the case of an atom, we have electrons moving to higher energy level, right?
Yes, ma'am.
And similarly, in this case, we have nucleons that move to higher energy levels, right? So this is a comparison just to explain, okay? So since this is a process that is unstable, there's a possibility that every entity tries to preserve its state of stability. In order to do that, it will decay rapidly to the ground state. Okay. So the excited states can reveal something about the orbits of individual nucleons. So this leads us to the concept that the individual nucleons can have orbits, right? Just like you have orbits for the electrons. Okay. So this has been explained also in your book, and you can read the detail over there. So we have the concept of single particle, and we have collective structure of nuclei. Just as we said before, that a nucleon is a single particle, but the behavior of the nucleon and the properties of the nucleon lead to the overall properties of the collective structure of a nucleus as a whole, right? Okay. So now I am going to erase the board. Okay. Is anyone there?
Yes, ma'am.
Okay.
Yes, ma'am.
Good. So I am going to erase this now. And we can continue. Excited states can be produced by adding energy to the core or paired electrons. Okay, so we can say, let us erase this part as well. Okay, so excited states can be produced by adding energy, right? You need energy for the nucleons to jump to higher energy levels. So if we are providing energy to a nucleon, to let's say the core or the paired nucleons that we have, energy to the core or paired nucleons, then we can produce an excited state. And this energy can take the form of collective rotation or vibration of the excited core, or it might even break one of the pairs. So there are different possibilities. So if a pair is broken, if you break this pair, then you will have the possibility to have a valence nucleon. So there are different things that can happen. So part of the goal of this nuclear spectroscopy is to observe. Now this is a phenomena that's known as nuclear spectroscopy. And the goal of this is to observe the possible excited states, observation of the possible excited states, and also to measure their properties. Okay. So what are the properties that can be measured? These properties, now we are going to talk of some of the properties that can be measured due to these excited states. In order to do this, I'm going to erase this board and go to the next page. Okay. Okay. So what are the properties that we can measure with the help of excitation? We can measure energy of excitation, right? We can measure the lifetime of this state. We can study the modes of decay. We can study the spin and parity properties. And we can study the magnetic dipole moment. And similarly, we can also study the electric quadrupole moment. Okay, so these are some of the properties that can be studied. Okay, so we have Tehreem is not in the class. So if I take the attendance, I have Durdana, Ramin, and Shurjeel. Okay, so I'm going to
Yes,
mark
ma'am.
the attendance for these three people. So I think Asad maybe had a internet issue.
Yes, ma'am.
Yeah, looked like that his voice was breaking. So Asad internet problem. Okay. Okay. Right. So let's erase these properties that we just talked about. Okay. So considering, let's say, 1,000 seconds of individual nuclides, each having hundreds of excited states, of course, we know that the number of nuclides is large, okay? When such a spectroscopy is performed, the large number, which is like thousands, okay? And we know that the excited states also is a large number, which there's a possibility of hundreds of excited states. So therefore, the task of studying this, which means the measuring of this, if you're performing an experiment, so measuring, tabulating, and then interpreting and calculating, this data will be overwhelming. So there will be a lot of data that will have to be calculated, interpreted, and then understood. So this is not an easy task. In fact, it's quite an extensive task. If nuclear excited states have to be studied, but people have been working on it and they've been studying it, and some data has been compiled that has been presented in your book. And if you look at this, you can see a table, okay, in your book. This is okay. So this is figure 3.19, where you can see the nuclear level schemes. So in this case, you can see a diagram like this, where you can see the energy in MeV. And you can see that this energy varies from 0 to different values that have been marked on this. So like 1.5, 1.2, and so on, 2.0. And you can see this is, for example, you have one value for bismuth, which has 83Z and 209A. So the value corresponding to this is 9/2 minus. Similarly, you have another excited state somewhere. I'm not drawing it very accurately. You can see the actual diagram in your book. So I'm just giving you an illustration of how these excited states are. And also there are other examples for, let's say, tantalum, for tellurium, for osmium. So you can see these examples and these diagrams in your book. Okay, and there are some experimental techniques that can be used to study these excited states. The experimental techniques include techniques that we use to study radioactive decay. And we perform nuclear reactions in order to study these techniques. Okay. Now, I would remind you that what I have been talking about is available in Crane. Okay, so this is chapter 3, the last article. And you can read this in detail and also pay attention to page 76, for example. So these are the last pages of this chapter. Also, in order to understand these, like we know that in chapter 2, we have some explanation. This is on page 40, which relates to article section 2.8 that explains the transition between states and some parameters related to that. Okay, so you can read some explanation here. And here, for example, we have an explanation of how such excitations can take place, and for example, the decay probability or also the transition probability. For example, it talks about transition between states. So it talks about the like, for example, different parameters like lambda, which is known as the decay probability or transition probability. Now remember that the symbols sometime in nuclear are different than in general physics. In general physics, normally lambda is the wavelength. But here in this case, lambda represents the decay probability or the transition probability. Okay?
Yes, ma'am.
Right. And there's another parameter here in chapter 2 in this same page that explains the quantity tau. Tau is defined as the lifetime of this state, of the excited state. Okay. And similarly, you have a difference in energy, of course, will be the difference in EF minus EI, the final energy of the state and the initial energy. And this will be emitted, for example, in the form of radiation. So we can say that delta E is equal to EF minus EI, right? The energy difference, for example, delta E can be defined as EF minus EI. And also we have a quantity that's defined as the energy uncertainty. And again, this can be represented by the width of the state, which is a capital gamma. So these are some parameters that are explained in chapter number 2, page number 40. So this is just like an article 2.8. You can just read this for a reference in order to understand some of the terminology involved with this. So the remaining part that we have discussed has been taken from Crane, chapter 3, page. It's not just page 76. Actually, it's a few pages near the end of the chapter. So it's page 75 and page 76. And also there's this diagram that we just talked about, figure 3.19, that shows you the energy levels for some nuclei. Okay.
Yes, ma'am.
So you can look at the figure, which is 3.19. Is that clear?
Yes, ma'am.
Good.
Yes,
Okay.
ma'am.
Now, another, so you study one page from here, from chapter 2 for this article. You study 2 pages from Crane chapter 3. And in addition to this, I have given you a handout. Okay, this handout has been uploaded to Moodle. Okay, so to WhatsApp. Okay, handout number 2, and I've also placed it with the S-Block photocopier. Anyway, if you cannot go there now, but anyway, it's also available in the PDF soft form. And in this handout, you also have some explanation of nuclear energy levels. The only difference in this case is that the symbols are slightly different. As I told you before, that when we read from one book, there's a given set of symbols. Sometimes when we read the same topic from another book, the symbols might slightly change. For example, you remember that in Crane, we use these symbols I raised to pi. In this book, we have the symbols. In this handout, for example, they are using the symbol j raised to pi, but the meaning is the same. Okay? Right? So they have given this examples. You can look at it. Okay?
Okay, ma'am.
Yeah. Okay, right. So this is again, you have one page on this topic. So this is enough information for this topic. And now I'm going to move to the next topic. So I'm going to erase the board. Okay?
Okay, ma'am.
Yeah. Okay. So okay. Right. Okay. Now there's another thing I would like to tell you. You know that when we are using Zoom, it normally disconnects after about 40 minutes. You know this, right? Hello.
Yes, ma'am.
Yeah.
Yes, ma'am.
Yes, ma'am.
Yes. So Zoom, in case Zoom disconnects, then I would ask you to click the same link again and we can continue the meeting. Okay? So please remember to do that.
Okay, ma'am.
Yeah. Okay. So let me also just confirm your attendance again. So Asad is with us now.
Yes, ma'am. Actually,
Okay,
my
so
internet just
yeah,
dropped off for a while.
I could understand that your voice was breaking. Also, Ayman is with us. So we are only missing.
Yes.
Yes, we are only missing Tahreem at this time, right? Okay. Right. Now, the next topic, another thing I would like to tell you is that you are working on your assignment. It's closing today, right? At what time? The assignment is closed.
Yes, ma'am.
It
It's
has
already
been
closed.
closed.
What was the time limit for that?
3 at 3
At
p.m.
3 p.m. it closed before the class, right? So the next assessment would be the quiz, okay? The quiz will be similar to the assignment, but the time will be shorter, okay? Because I've given you a longer time to solve the assignment, but for the quiz, I will give you maybe 1 hour, something like that. Okay, I will open this for about 1 hour. Okay. I've
So, ma'am, we
already,
will have same numerical problems.
yes, you will have problems. And in this case, you will have to sit during the hour that it's open. I will send you the exact time on that day. And we will also, what's the date for the quiz? We've also already made the assessment plan. What was the date we decided for the quiz? I think it was the 1st of December, right? You remember that? You remember
Now we
that?
have to see.
You have to see. Right. So I am just reminding you, actually, I've already announced this in the class, and I've also, here, I can show it to you. Let me share it with you again. So I can do it. So I can share this. Okay, share. Can you see it now? Can you see the system?
Yes, ma'am.
Yes, you can see it now. So you can see that the quiz is on the 1st of December, which means on next Tuesday. Okay. So on next Tuesday, I will open this during the class time. Okay. Is that clear?
Okay, ma'am.
So during the
Okay.
class time, I would like you to attempt this.
Sure, ma'am.
Okay. So next Tuesday, again, if anyone is absent today, everyone is present except Tareen. So you can remember that 1st of December on Tuesday, this quiz will open during the class time, and that's the time when you will solve it. Okay?
Ma'am, then syllabus will be the whole syllabus we have covered so
Syllabus
far.
will be based on what we have studied, which are the first 3 chapters plus the 2 handouts. Okay?
Okay, ma'am.
Okay.
Okay, ma'am.
Okay, right. So now I'm going to share the whiteboard again with you. So new share and the whiteboard. Okay. So here we have it. And so this is 1 hour. This was 1st of December. This is Tuesday during class time. You will solve it. Okay. So the class time, you know the class time, right? It will be in MCQ format. I will make questions based on the material that we have studied, which is the first 3 chapters plus the 2 handouts. Okay,
Okay, ma'am.
right. Now I'm going to erase the board again. Okay, and now I want to move to the next topic that we are going to do. And this topic is, I'm going to start a new, completely new topic, and this is called nuclear reactions. Okay. For this topic, I'm using the book Kaplan. Okay. And in Kaplan, this is chapter number 16. Okay.
Okay, ma'am.
Okay. Now, so what are nuclear reactions? A genuine nuclear reaction can be represented schematically as X plus capital X will give you Y plus small y. So in this case, small x is the incident particle. And it's also called the bombarding particle. So to start a nuclear reaction, you need to bombard a particle. Again, like I said, symbols can vary from book to book. So at this time, I'm explaining these symbols. So capital X here represents the target nucleus on which the particle is bombarded. Capital Y is called the product nucleus. And small y is called the emitted particle. Okay. So if you want to represent this in a compact way, the compact notation will be X, X, Y, and Y. So this is the way you write it. Okay. Okay. So in this case, small x normally are elementary particles or gamma rays. So these incident particles are normally in the form of elementary particles or gamma rays. Okay, and X and Y. So I'm going to erase this part. Okay, no. Let me write this all together again. Okay. So the incident X and Y, actually X and Y, the incident particle and the emitted particle normally are elementary particles or gamma rays, elementary particles or gamma rays or nuclei. For example, alpha particles or deuterons. What are alpha particles?
Helium nuclei.
Yeah, so they are nuclei. So it's an example of a nuclei, but we also call it a particle sometimes, right? Okay. And also, why the emitted particle, we can have more than one particles, okay? More than one particle may be emitted as a result of a nuclear reaction. Okay. So there's another term that I would like to discuss, and this is okay. So the other term that I would like to discuss is the term called transmutation. So what is transmutation?
The conversion of one nuclei into another.
Okay, it can also be the changing of one element into another by processes such as the changing of one element, because it's not just happening to one nucleus, right? So it can be more than one nucleus, right? So it's the changing of one element into another by a process such as radioactive decay. You know that as a result of the decay, one element may change into another element, right? And it can also happen as a result of nuclear reactions, which include nuclear bombardment or another similar process. So this is the definition for transmutation. Now let us talk about an experiment, an example for such a process. So in this case, we can consider the example of the famous experiment that is called the Rutherford's experiment or Rutherford scattering. So in this case, we can talk about an example. So what did Rutherford do? Rutherford performed the transmutation of elements So as a result of, he did this by scattering, alpha scattering, right? By alpha scattering on nitrogen. And where did he get the alpha from? He got the alpha from a radio, huh?
From polonium?
Yeah, from a radioactive polonium source. So this is an example of a nuclear reaction. And this reaction, according to this notation, can be written as alpha plus N14 will give you another new nucleus, which is transmuted. So this is oxygen 17, and the particle emitted will be a proton. So this is an example of such a reaction. So there are now certain laws that are obeyed in such reactions. So what are these laws? Let's look at them. So these are called the laws of conservation. For nuclear reactions. So in this case, we can talk about a law of mass conservation. So this one is the total number of nucleons in a nuclear reaction is conserved. So in this case, we can write that sigma A is equal to a cost. This is a standard law that is followed in this case, and you can observe this in any nuclear reaction that you study. And then there's another law, which is the law of charge conservation. So in this case, the total electric charge capital Z in a nuclear reaction is conserved. So in this case, we can say that sigma Z is equal to constant. Okay.
Okay, ma'am.
Okay, beta. So I'm going to erase this now. Okay. So we have talked about two laws. Okay. I'm going to erase them and then write the next law. Okay.
Okay, ma'am. And I think our meetings is not going to end as we have.
Yeah, because they
Limited
sometimes give you a bonus meeting.
Yes, ma'am.
So I think we are getting that today. So you're lucky.
Yes, ma'am.
But anyway, there's a trick that I've learned about, and we can try that out. And that is that if you click the same link the second time, the meeting continues. The same meeting continues. We don't have to, schedule a new meeting. So we can try that whenever it ends. Okay. If not today, maybe next time. Okay. So,
Yes, ma'am.
so conservation of linear momentum. So in this case, the total linear momentum in a nuclear reaction is conserved. So these are very simple laws. So we can say in some books, the symbol for linear momentum is M, and in some books, the symbol for linear momentum is P. So whatever it is, right? you can use any of these symbols. Okay. And the fourth one is the law of conservation of angular momentum or spin. So in this case, we can write that sigma J is equal to constant. Again, some books are using the symbol capital I and some are using the symbol capital J. And now I'm going to erase again. Okay, so now we're going to go to the fifth law. Yeah. So in this case, the law of conservation of mass energy. So in this case, we have the total mass energy in a nuclear reaction is conserved. So in this case, we again, mass energy can be represented as, in some books, it's represented with T or it's represented with E. So this plus m naught c squared is equal to constant. So T in Kaplan is normally used for kinetic energy. And m naught is used for the rest mass. Okay, I'm going to erase this now. Okay. Okay. And now the sixth one is the law of conservation of parity. Okay. So parity is conserved in nuclear reactions except in weak interactions. Like beta decay, for example, right? Okay.
Yes, ma'am.
Okay. And physical quantities that are not conserved in a reaction are not conserved in a nuclear interaction. Okay, our magnetic dipole moment. Which is mu I, and electric quadrupole moment, which is Q. Okay, so we have discussed the laws of nuclear reactions. We have discussed 6 laws of conservation for nuclear reactions. We've talked about the law of mass conservation, where the total number of nucleons in a nuclear reaction is conserved. So in that case, sigma A is equal to constant. Then we talked about the second law, which was the law of charge conservation, in which the total electric charge Z in a nuclear reaction is conserved. So sigma Z remains constant. Then we talked about conservation of linear momentum. The total linear momentum in a nuclear reaction is conserved. And in this case, we use the symbols either P or capital P or capital M to represent linear momentum, and hence sigma of the linear momentum is equal to constant. Then we talked about the fourth law, which is the law of conservation of angular momentum, which is also called spin. And in this case, like we said, some books are using the symbol capital I, and some books are using the symbol capital J. So the sum of all this, sigma J, is equal to constant. And then we talked about the law of conservation of mass and energy, in which case this is the sum of the kinetic energy and the rest mass energy of the system should be constant. So we know the rest mass energy is based on the Einstein's equation, which is a product of the rest mass m naught multiplied by the square of the speed of light. And then we talked about parity conservation. Parity is conserved in most nuclear reactions except in weak interactions. And then finally, we talked about some quantities that are not conserved, and these include the magnetic dipole moment and the electric quadrupole moment. Okay, so now I'm going to erase this. And now I'm going to talk about the types of nuclear reactions. Okay, so we can talk about a reaction that is called the photodisintegration reaction. So in this case, okay, so in this case, we have photo means what? The incident particle will be a gamma photon. Okay, gamma is a photon, right? The word photo
Yes, ma'am.
comes from photon, and gamma is a photon, and therefore this reaction is called a photodisintegration reaction. So we can write this reaction as gamma is the incident particle plus a target nucleus, which will give you some product nucleus plus emitted particle. So an example of such a reaction can be, let's say, gamma plus H2. This can give H1 plus neutron. H1 and H2 are the isotopes of hydrogen, right? So this is one example. Now we can talk about another example, another type of reaction. So this can be radiative capture reaction. So we can talk about radiative capture reaction. So radiative capture reaction, if the emitted particle Y is a gamma photon. In this case, the emitted particle Y is a gamma photon. Then this reaction is called a radiative capture reaction. So example again will be, the general form would be an incident particle plus a target nucleus will give you a product particle plus gamma, gamma being the emitted particle. So an example for this can be, for example, if H1 is bombarded on lithium 7, then you get beryllium 8 plus gamma. So H1 is also called a proton, right? So H1 means, H1 nuclide means, H1 nuclide means there's only one nucleon, which is a proton. So H1, it can also be called a proton. So you're bombarding a proton on lithium and you're getting, as a result, another product nucleus plus a gamma photon. And hence this is an example of a radiative capture reaction. Okay, now I again clear the board and we can go to another type of reaction, which is called scattering reaction. So scattering means when X is equal to Y, which means the incident particle and the emitted particle are equal, and the target nucleus and the product nucleus are also equal. The reactants and the products are the same. So the reactants, these are the reactants, and these are the products. Both remain the same. Okay, and such a reaction is called a scattering reaction. Now we know that there are two types of scattering. One scattering is called elastic scattering. And the other scattering is called inelastic scattering. Now, what is elastic scattering? Elastic scattering means that the total kinetic energy of the reaction is conserved. Total kinetic energy of the system is conserved. So, some kinetic energy is usually transferred from the projectile to the target nucleus, but the latter is left in the same internal or nuclear state as before the collision. So the collision between two billiard balls, for example, in which neither ball is damaged or changed, is an example of an elastic scattering. And in this case, the product nucleus is in the ground state. So this is an example of the elastic scattering. The second case is the inelastic scattering. So inelastic scattering means that the target nucleus, which is capital X, is raised into an excited state. So this, which we can call X star. And this will be, an excited state is always an unstable state. And the total kinetic energy of the system decreases by the amount of the excitation energy given to the target nucleus. So the total kinetic energy decreases by an amount equal to the excitation, by an amount of the excitation energy of the target nucleus.
Ma'am, can you please explain inexcited scattering again?
Okay. So inelastic means, okay, elastic means that when the total kinetic energy is conserved, right? So elastic means that both the target nucleus and the product nucleus are in their ground state, okay? And the total energy of the system remains constant, okay? So it's a stable system, right? Inelastic scattering means that the target nucleus is raised to an excitation state, which is represented by a star, as you can see, okay? This star. So
Yes,
when you
ma'am.
have star, it represents an excited state, and an excited state is an unstable state. And in order to reach an excited state, you need some energy to take a nucleus from its ground state to its excited state. And therefore, you have a loss of the kinetic energy, and hence the kinetic energy is not conserved in this case. Okay? So we can write this as in notational form as x plus capital X will give you an excited nucleus X star plus the particle remains the same. So this is an inelastic scattering. The excited product nucleus usually decays very quickly to the ground state with the emission of gamma rays. You know that since this excited nucleus X star is unstable, so an excited nucleus always tries to de-excite. So the way for a excited nucleus in nuclear reactions is normally by radioactive decay, whereby this nucleus will emit some radiation in the form of most probably gamma rays. It will give off the extra energy that it has in the form of gamma rays and come back to its ground state. So this is an example of inelastic scattering. Okay,
Okay, ma'am.
good. So let us now
Okay,
erase
ma'am.
word. So let us erase this.
Okay, ma'am.
Wait a minute. Okay. Now there's another thing we can talk about, and this is called the Q value of a nuclear reaction. This is again from the same book, Kaplan, page 261, page 262. Kaplan, page 261, 262. So in this case, the Q value of a nuclear reaction is also called so this is also called the nuclear reaction energy, which is also called, this is also called nuclear disintegration energy. And this is also called the energy balance of the reaction. Okay. So in this case, we can again consider a nuclear reaction to explain this. So consider a nuclear reaction. Which is x plus x will give you y plus y plus a certain amount of energy that we call Q. So this is the Q value that we are talking about. So the Q value of such a nuclear reaction is absorbed. So Q value can be positive and it can be negative. So this value Q can be greater than 0 or less than 0, which means it's positive or it's negative. Okay. So now I'm going to erase this. Okay, right. Okay. So in this case, if it's an exothermic reaction, then we can say that Q is greater than 0 or Q is positive, or we can call it an exoergic reaction. And in this case, we have the production of heat. Energy is released. Production. The nuclear reaction results in a production of heat. Results in a production of heat. Normally, the way the energy is released is in the form of heat energy. And then you have the second case, which is the endothermic reaction. In this case, we have, this is also called endoergic reaction. And in this case, Q is less than 0, or we can say Q is negative. And this is a process in which heat is absorbed. You know that for performing certain reactions, you have to provide heat energy to the system before the reaction takes place. So they're the opposite of each other. In this case, it will give you heat. In this case, it will take heat in order to start. Okay?
Yes, ma'am.
Right. Okay, so you can erase this. And now we can try to understand how this value works. So in order to understand this, we can start with the standard equation that we have. So let's try to derive this value, the expression for this value. So derivation of Q value. So in this case, we can start from x plus x will give you y plus y. Let us say this is equation number 1. Let us assume that this x is initially at rest. Okay, and so if it's initially at rest, this means that the kinetic energy is equal to 0. And also we know that the total energy of a particle or an atom is the sum of the rest energy and the kinetic energy. Therefore, the statement that the total energy is conserved in the nuclear reaction means that we can write the equation in the form of the energies of all the elements present in this equation. So if we try to write that, we will get what? Let us go to the next page and write that. Okay, so see. Okay, so we can again keep in mind that x plus x is equal to y plus y. And therefore, we can then write the equation as Ex plus mx c squared plus mx c squared is equal to Ey plus my c squared plus Ey plus my c squared. So this we can call this equation number 2. In this case, E represents kinetic energy, right? And M, small m and capital M represent the masses. Again, we are using small m to represent the incident particle and the emitted particle mass, and capital M to represent the target nucleus and the product nucleus. So I think I will stop here today, okay? And then we can continue from here next time. Again, remember on Tuesday during the class time, you will be having your exam.
So we won't have Tuesday's lecture, right?
Right. So please prepare for that. And I will upload it and you will perform it. I'll keep the timings according to the class timings. Okay?
Okay, ma'am.
Okay, thank you.
Okay, goodbye, ma'am.
Goodbye, beta.
Goodbye, ma'am.